Okay, so we're going over section 2.2, separable equations. We're going to do the separation of variables technique here. All right, and I'm going to just let you copy. I'm going to talk, but let you copy. So, you saw in section 2.1 some differential equations that, I mean, some of them can be solved, but some of them could not be. And at any rate, any differential equation, you're able to graph its direction field and see how certain solutions, how solutions will behave. Okay, and eventually, when we get into section 2.6, Euler's method, we'll learn also how to approximate values of a solution to a differential equation. Right now, we can see what solutions look like, but we also want to approximate values of the solution, and that's going to come up in section 2.6. But in section 2.2, we focus on differential equations. The ones that I'm assigning are ones where you can explicitly find solutions. Okay, so all right, take a moment here. Okay, so we want to find the general solution of this differential equation. And we want to use an approach called separation of variables. Now, we have here two variables, a variable y and a variable x. Which is the dependent variable? Would it be variable y or variable x?
Y.
That's right, Thomas. Y is, because we have a dy dx, y is understood to be a function of x. So let's go ahead and try to solve this differential equation. All right. No, I'm not writing. I'm moving to the next page. Okay, exactly. Okay, so we're going to separate the variables. So what I want to do is I want to get y variables on one side, x variables on another side. So first thing I'll do is I'll factor the right side. Separating variables involves a lot of factoring. Let's see, Michael, maybe log back in. Yeah, try rejoining, Matthew. Thank you, Matthew. Try, if a page is ever blank, just log out and come back in, and that usually solves the problem. Okay, so now what I'm going to do is right here, I'm going to multiply both sides of this differential equation by dx. Okay, so what I did was on the left side, I multiplied by the differential dx. And on the right side, I multiplied by the differential dx. Okay, and so this gets me here. Now what I'm going to do is I'm going to divide by x squared both sides. And I'll get here. And then I'm going to divide both sides of the differential equation by the variable y. And that gets me here. Let me know, please, if you have any questions. Okay, excellent, excellent. All right. On the right side, I'm going to rewrite the 1 minus x over x squared. I'm going to write that as 1 over x minus 1 over x squared minus 1 over x. So what I did was I took, 1 over x squared. I split this fraction. It's a single fraction with a, so I'm going to write it as the difference of two fractions. Okay, and x over x squared is 1 over x. And now at this stage, we've separated the variables. You have y variables on the left side and x variables on the right side. Okay, and just ignore that ringing. Okay. A lot of people call who I don't want their, I'm going to get these like robot calls. I mean, it isn't even people anymore. It's like robots calling. That's even more disrespectful. Yeah, Christopher and Matthew know what I'm talking about. Okay, well now that I'm here, now that I've separated the variables, what do we do now? What are we going to do to both sides of the differential equation? Integrate both sides. Excellent. That's what we're going to do. Good, Matthew. Good, Christopher. So that gets me here. If I integrate the left side of the equation, I have to integrate the right side of the equation. Okay. Well, and now let's go to the next page. So I decided to rewrite these fractions as exponential terms. Didn't have to do it. And let me see, there was a chat here. Zachary, you're almost right. Zachary chatted out what the antiderivatives are, and he's almost right, but the integral, the antiderivative of y to the negative first, is the log of, what are these symbols here? Absolute value. Good, Ann. So the antiderivative of 1 over y is the log of the absolute value of y plus a constant of integration, because these are indefinite integrals. And then, of course, we get these antiderivatives on the right side, okay, plus another constant. Now, I don't want to have two constants to worry about. Okay, but I'll mention in my work, this is important because for the exam you'll be submitting your work. Obviously, you can't have the same constant. Well, what I want to say is the constant of integration on the left side and the right side can be the same, but they can be different too. So that's why I have a C1 and a C2. But what I do is I subtract the C1 over to the right side, So C2 minus C1, and I'll call that C3. I'm renaming the constants constantly throughout the problem. Okay. And so now, this gets me to this step here. Are there any questions so far? All right, all right. Well, we want to solve for y. On the left side, I have the log of the absolute value of y. So how am I going to solve for y? What do I have to do to remove the log on the left side, that natural log? That's right, Christopher. We have to exponentiate both sides. And that's what we do. We exponentiate both sides. Right? Okay, Zachary. Yeah. Let's see here. Forgot the E though in your chat, but don't look. You see what's going on here. I know you're on the right track. So, okay, I exponentiate both sides here, and now that's going to remove the e to the log of the absolute value of xy just gives you absolute value of xy. But on the right side here, on the right side, we're taking e and we're raising it to this power here. Negative x to the negative first minus the log of the absolute value of x plus c3. But remember, e to the a plus b equals e to the a times e to the b. So I can write the right-hand side as the product of three exponential terms. Are we okay up to here? Are there any questions? All right, Andre's good. Matthew's thinking a little bit. All right, Anne's good. Okay, Kaye's good. All right. Oh, okay. Oh, so what I do, okay, what I do here is there's a reason I'm did this. So I have here, the negative log of absolute value of x. I can write that as -1. Well, this here is just -1 times the log of the absolute value of x. Okay, no problem. And what I'm going to do here now is this term here, I'm going to rewrite that exponential term as e to the log of the absolute value of x to the negative first power. And there we're using the rule that the log of, a to the bth power equals b times the log of a. How many recall that from their pre-calculus days? And that's what we did. Yeah, and why does that help us? Well, if I write the exponential term this way, the e and the base e and the log simplify out, and you're left with the absolute value of x to the negative first. Okay. And also notice this e to the c e to the c constant C3, I call that C4. So it's important to keep track of the constants. Some professors might be a little sloppy with that, but it's very important to keep track of those constants. And I do look at that. All right, are there any questions? Shall we continue to the next page? No, we have more to go, Matthew. Because, good question. I want to know what y equals. I want an explicit solution for y. Right now, I have the absolute value of y, but we gotta take care of that now. So okay, let's go to the next page. So I write the absolute value of y as the constant C4 times the absolute value of x to the negative first times e to the negative 1 over x. Okay, and I can write that on the right as a fraction. And the only thing we have to worry about now is removing the absolute values. Okay, we have to deal with those absolute values. Again, you know, well, yeah, we have to deal with it. So what I do is this. What I do with this, I take both sides of this equation and I multiply by the absolute value of x on both sides. So then on the left side, I get the absolute value of y times the absolute value of x. And that's just the absolute value of x times y. Okay, that's what I get on the left side. And so that means that x times y has to equal plus or minus C4 times e to the negative 1 over x. That's what it has to equal. Now, you know, what's going on there? Why is that true? Well, you know, sometimes it helps to take a little analogy here. Let's say you had the absolute value of a equals 3. If the absolute value, and this is just a little example, absolute value of a equals 3. If that's true, then what is a equal to? Good, 3 or negative 3. Good, Matthew, good, Andre. That's right. Okay. All right, well now let's say I have the absolute value of an apple. Absolute value of an apple equals a pear. Okay, absolute value of an apple equals a pear. Well, what would the apple then have to equal? Good.
Or an apple.
Plus or minus pear.
Plus or minus 4, okay.
Well, here's the thing. All I'm trying to do is justify this last step here. Christopher's comfortable with it. So on the left side, the absolute value of xy is like the absolute value of my apple. And then on the right side, C4 times e to the negative 1 over x power, that's like my pear. And so if you're you know, good with this, should be good with this. All right, but we're not done yet. Not done yet. May I move to the next page on the solution? Oh, it doesn't matter what's inside that absolute value.
1 second.
Yeah. Okay. Okay. We're going to go forward. I'm ready to move to the next page when you are. Mark, I can go back to that, but let me, so you mean Mark's asking about the -1 in front of the log of the absolute value of x? Is that what you're asking about, Mark? Yeah, it's just the, yeah, that's, Matthew chatted it out. That's how, you know, always after class too, you know, we can, you know. All right, let's move on then.
Wait, I have a quick question.
Oh, wait, hold on. Oh, there's more below. Man, I'm sorry. Okay,
Yeah,
I see. So, all right, hold on. Let me take a look here. Hold on. So the plus or minus C4e to -1 over x on the right, that's the same as taking plus or minus C4 and multiplying it by e to the -1 over x. I mean, I can write this way. But the plus or minus C4, either it's a plus C4 or a minus C4, regardless, it's a constant. And this is going to be the final constant that I am going to be needing. In other words, I'm not going to be, the constant's not going to be getting transformed anymore. So when that's the case, I put in a capital C. And WebAssign's going to want capital C. Traditionally, it wants a capital C for its constant. So that means x times y equals c times e to the -1 over x. And so y equals then the solution. This is the answer, class. Y does equal capital C, that constant, times e to the -1 over x divided by x. And of course, if we wanted to determine, that represents a family of solutions, right? That this is a general solution to the differential equation. It's a family of solutions. In order to solve for a constant, what would we additionally need to the differential equation in order to solve for that constant?
Yeah, we can't solve for that C because the plus or minus is like unambiguous from like earlier portions.
Well, but no. Well, if we had an initial value, we could solve for the constant. But this is, of course, this is a general solution. This is a family of solutions here. But if you give me an initial condition, I'll be able to solve for a constant. But different initial conditions will have different constant values.
I guess I meant like this constant value doesn't allow you to solve for the previous constant values. Like maybe like you can't solve for C4, C3, C2, or C1 with this C.
I think you could. I think you could go backwards. I think you could, but who would want to? All we care about is you know, getting that. In other words, if I say, your question's a good one, Matthew. If I said like y of 0, can't do y of 0, right? Because there's an x in the denominator. So solution would be defined at x equals 0. But if I said y of 1 equals 4, okay, hold on. If I said that y of 1 equals 4, then I would substitute 4 in here and 1 for x here, and I would solve for this constant.
Okay, I guess I'm just saying like I don't know what the point is of including the constant. I guess you have to keep track of where it is, because
Yeah. Well, it's just good math, you know, and I'll tell you, let's do another example, and you'll start appreciating it. I would hope all professors do rename the constants. I don't know in calculus too if your professor did, but it is good mathematical practice to do so. But that being said, let's get to another problem. I want to try to do 3 of them so that you see a variety, a good variety. Okay, let's look at this one here. Let me give you a moment to copy this one down.
I guess I'm just saying like it's pointless to do the like C2 minus C1 or whatever if it's just going to be a constant at the end anyways.
No, sorry, I was talking in about, yeah, it's not pointless to say C2 minus C1, but in the future, we know that when we integrate both sides of the, when we start our integration, we're going to have constant of integration on the left and the right. So, and we know we're going to then have that then on the right. We're going to combine those constants of integration, and it'll be on the right side. So we won't need to do the C2 minus C1 step again. I just did it once so you could see it, but we know that always has to be done. Look
Okay,
at the,
okay.
yeah. So here, dy dt equals y squared minus y. Okay, we want to find the general solution. This is a separable differential equation. Okay, so let's go ahead and begin the solution. So I'm going to multiply both sides of the differential equation by dt. And that gets us here. And then, again, I want the y variables on one side and the t variables on the other side. So I'll divide both sides by y squared minus y. And now at this stage here, we have separated the variables. We've separated the variables. So what comes next? What do we do now? Integrate. Good. Good, Christopher. Integrate both sides. And I can almost hear the left side telling me to do something with y squared minus y. It's almost we can almost hear it talking to us, that side. Intuitively, in your math intuition, what do you want to do with y squared minus y? You want to factor it. That's right, Justin. Good. That's right, Matthew. Good. You want to factor it. Okay. And now it's time to integrate. Well, I like Christopher having a number in front of my differentiable. Christopher's asking about having the 1 there. I mean, yeah, you could just have integral of dt, but I don't know. I always like there to be, and it's understood there's a 1 there, so why not put it there? You know, what are we afraid of, right? Oh wow, you know, this left side, to integrate that left side, oh wow. I think you've seen that kind of integration in calculus too. What procedure? Use substitution. Zachary, I wasn't thinking of use substitution. I'm not going to use integration by parts on it, that's for sure. What other things did you learn in calculus 2? When the denominator is a product of two factors. I'll give you a hint. Begins with a P.
I have
we can
Okay.
tangent function, the inverse tangent. I think I know.
No. So
We
this
can
is
use-
like Wheel of Fortune here.
No.
2 words.
Partial fraction.
There you go. Partial fractions. Good, Christopher. So
I have a quick question, actually, Professor.
yes.
Can you go back to that one slide?
Sure.
Shouldn't, where it says or, shouldn't it be a 1 over y times y minus 1?
Oh man, I have it. Oh wow. You're right. You're right. Good catch. This should be y times y minus 1. Yeah, please make that correction, class. Hold on. Hold on. This should be y times y minus 1. Okay, let me see here. Now that's gonna change things a little bit here. Hold on. Okay, okay. All right. So I'm going to have to continue this on the let me see here. All right, let me continue it on the black on the the whiteboard. All right, so let me continue it here. Hold on. All right, here we go. So now I have 1 over y times y minus 1 dy equals, thank you for catching that, Christopher, equals the integral of 1 dt. And we're going to use partial fractions. So 1 over y times y minus 1 is going to equal, we break it up into something over y plus something over y minus 1. What goes over, so these are both linear factors. So what are we going to put over the y? Right, we put an a, good, Zachary, and over the y minus 1 we put a b. So what we're going to do is we're going to solve for a and b. So we're going to multiply through both sides of the equation by y times y minus 1. And that means 1 will equal a times y minus 1 plus b times y. Okay. So we multiplied through this equation by y times y minus 1. And so the left side reduced to a 1, and then you have the two terms on the right. So that means 1 will equal a times y minus a plus b times y. And so 1 is going to equal, hold on here. 1 is going to equal a plus b times y minus a. Okay, let me just check one thing here. Okay, so we need, for this equation to be true, the left side needs to equal the right side, right? The left side needs to equal the right side. So what does A plus B have to equal? 0. Good. Good, Zachary, because there's like 1 is like 1 plus 0y. And then what does the negative a have to equal? Well, negative a is a constant. What must negative a equal? Has to equal 1. Has to equal 1. Okay. Are there any questions so far? Let me know if there are any questions so far. So from this,
Explain that one more time.
yes, Paige. So we're equating the left side of this equation here. We're equating the left side to the right side. So the left side, the y term, that if the left side of this equation equals the right side, then the y term on the left has to equal the y term on the right. Well, the coefficient of the y term on the left is 0. The coefficient of the y term on the right is a plus b. So a plus b would have to equal 0. It has no other choice. On the left side also, we have a constant, 1. Well, that would have to equal the constant on the right side, which would be negative a. So a plus b has to equal 0, negative a equals 1. But this means then that a must equal negative 1, and then b has to equal positive 1. And so now you've determined the values. You've determined the values of a and b.
Thank you.
Okay, so you're welcome. And so now we go back to our integral. We go back to our integral here. And we have, let me just see here, one moment. Right, we have negative 1 over y, negative 1 over y, plus 1 over y minus 1. And I'm doing this live, so check my math, but I got 20 students checking math, so hopefully, but this is what we get. And on the left side, we can integrate this left side. The left side is going to be negative times the log of the absolute value of y plus the log of the absolute value of y minus 1. Okay, and that's going to equal then t plus a constant of integration. I'll call it C1. So I know from this step, when I integrate the left side, I get a constant of integration. When I integrate the right side, I get a constant of integration. But I know I would bring the constant of integration from the left side over to the right, and that's so this step is fine. Hold on, there was a chat here. Hold on. Well, what I'm saying, Zachary, is just in your mind, pretend that you have a C2 on the left side, and you subtract it over the right side, and then you get like C2 minus C1. I mean, you know, I guess I could call this C3, but it's fine just to, we know there's a constant. We know that when we're done, we're going to have a constant on the right side. Is that good, Zachary? Is that? Okay, wonderful. Now, on the left side, if you don't mind, what I'll do is I'll write this as the log of the absolute value of y minus 1 minus the log of the absolute value of y. That equals t plus that constant. And again, my goal is to solve for y. So on the left side, I have a difference of two logs. We know there's a rule when you have the log of a minus the log of b, that equals the log of a over b. Okay, so that's what you have here. Okay, so far so good? Are there any questions up to here? All right. Well, it's going to be good to, I mean, we have the absolute value of y minus 1 over the absolute value of y. So we can write that as the log of the absolute value of y minus 1 over y. So if I, you know, go back like, you know, start like on this side, I have the log of the absolute value of y minus 1 over y. And that is going to equal my t plus C1. And that's right, Matthew. Now we exponentiate both sides, and if we do that, we'll get the absolute value of y minus 1 over y equals e to the t plus C1 power. And this, of course, is e to the t power times e to the C1 power. E to the C1 power is just, I'll call that now C2. Okay, and so now I have the absolute value of y minus 1 over y equals this constant C2 times e to the t. Are there any questions up to here? All right. Right. Well, now, good. Thank you, Matthew. So now we got to deal with the absolute value. So y minus 1 over y is going to equal plus or minus that C2 times e to the t. Okay? The plus or minus C2 part I'll call now C. And so I have y minus 1 over y equals C times e to the t. All right. Now we have to solve for y. Let me kind of separate this here. So y minus 1 will equal C e to the t times y. And that means that negative 1 will equal C times e to the t y minus y. But this, we can factor the y out. Okay. Can factor the y out on the right side. And now just divide by that c e to the t power minus 1. So negative 1 divided by c e to the t minus 1 will equal y. That's your solution. That is your solution. All right. Are there any questions on that? And WebAssign will want it, I mean, you're going to get the explicit solution, and that's okay. Well, if you're comfortable, we'll go to our third example. Okay. Zachary, this is fine. This answer's fine. I mean, you could write it multiple ways. You could write it as let me see here. If you multiply top and bottom by e to the negative t, you could write it different ways, but this is the best we can do. Okay, Matthew's good. Are there any other good questions? All right. Well, then let us proceed on to the next example. Okay. Okay. No problem. Did I make? Maybe I made an let's see here. So are you talking about right here, Matthew, the factoring part? So there's a common factor of y. And so I factored it out. And so I write this as y times, no, not a divide. This is like a bracket. No, not a divide. I'm not dividing, just factoring. Okay, everybody's good with that? I'm just factoring. Factoring the right-hand side here. Okay, are there any other good questions? Okay. All right, let me stop sharing there and let's go to the last example. Again, I think these 3 examples I'm doing will, you know, you're still going to have to do things like integration by parts and things like that from, you know, substitution. You're going to have to use your integration techniques. But you know, you've had calculus too. And so, all right, let me give you a moment to copy this one down. All right, so, okay, let's see here. How are we going to handle this? Well, we need to separate the variables. So let's do that first. All right, are there any questions here?
Can you go back again, Professor, to the previous page, please?
Sure.
Thank you. Got it. Thank you.
All right, Thomas, very good. Christopher, you need me to go back to the previous page? Okay, you're good. Yeah, yeah, we're still here. Yep. Doing fine. Very good participation today. Very good participation. All right, so once we separate the variables, we know that we have to integrate. We know that's our next order of business. And so that gets us down to here. All right, very good. So let's see here. This is going to be interesting. What makes these 2 integrals difficult? what makes them kind of difficult to,
Square roots, I guess.
yeah, I agree, Christopher and Thomas, the square root is not too nice. So, hey, why don't we make a substitution on those square roots? So let's go to the next page here. So since both integrals are, I mean, they're both I mean, one's with respect to y, the other's with respect to z, but I'm going to do the left side, the substitution, and then the right side will follow suit. So I'm going to let u equal the square root of y. Okay, I'm going to let u equal the square root of y. And then, of course, u is equal to 1/2. And du dy is 1/2 times y to the negative half power. And that means du is 1/2 y negative half power dy. So, you know, with substitution, recall, we want to replace, we're changing this integral on the left. It's an integral with respect to y. We want to make it an integral with respect to u. So right now, the square root of y is a u. That's good. And I think you know that y would equal u squared then, right? But what's left to deal with is the dy. I have to get dy in terms of the variable u. And right now, I have that du is 1/2 times y to the negative half dy. What I'm going to do is I'm going to multiply both sides of this equation by y to the half power. That's what I do right here. Now, how does that help me? Well, look on the right side. You know, the right side, I want to get dy alone. I want to get dy by itself. Well, y to the half times y to the negative half. The base is the same, so you add the exponents. That gets you y to the 0th power. So you're going to get then, and incidentally, y to the half, remember, was u. So you're going to get here, you're going to get u du equals 1/2 dy. Hence, dy is 2 du. And similarly, on the right side, dx is 2z dz. So, you know, this is the kind of work I'll want to see on your exam when you show your work. You know, I need to see that you understand, that you know how to do it. Let me see. Hold on. Question. Well, Matthew, yeah, do like I'm doing. Sure. Yeah. And so here you go. But you know, you'll show the work like for this kind of problem, you would show the work, the same work I'm showing. I mean, you know, what else can you do? You know, that's the work. I mean, it is the work. We have to understand, you know, have to assess that you understand the concepts. And so look, now we get down to here. All right, we get down to there. And I'm going to go ahead and incidentally, I can divide the 2's out. The 2's can divide out. Are there any questions then? May I move to the next page? Kat and Kathy is good. Okay, all right. All right, Antonio, very good. What's that mean, Matthew? IDK? Oh, you're good, but I don't know about others. Okay, all right. Got it. All right, so here we are. I divide the 2 out. And the denominators, I factor the denominators. So the denominator here, u plus u squared is u times 1 plus u. Well, you see that right down here. And now the u's and the z's simplify out. See, when I do my math, I always show, it's important to show the work. I'm going to expect you to show the work. And, it just is, it's what everybody should be doing, right? Because I have to make sure I like to see that you're comfortable with the concepts. Hold on here. Let me see, a half, where mark, what, so these 2's, I divided both sides of the equation by 2, and those went away. Okay, good, good. And so then, the antiderivative of 1 over 1 plus u is the log of 1 plus u. I do the same thing I did in the last problem, basically. Same kind of thing. And I get down to this step here. We're almost done, class. I'm gonna, I got delayed a little bit for that second problem, but we're doing fine. I only need a few more minutes. If you can stay, I appreciate it. If you have to go, I understand, but I'm only gonna need a few more minutes.
Professor, why is the
Yes.
constant only on one side?
Well, what happened was so like when I integrate the left side, okay, so like technically there's a constant here, okay, and there's another constant here. And I'm going to subtract the constant from the left to the right. So on the right, I have C2 minus C1, and I would call that constant C3. And we did that for the first example we did. But we know every time we integrate both sides of the equation, we're going to get when we combine the constants, we're going to get a constant on the right side. And that's the reason I just put a constant on the right side. Is that all right, Paige? Is that all right?
Yes, thank you.
Okay. May I go to the next page? We're right here. All right. So now I exponentiate both sides. And then e to the c first power is c2. And then, of course, I have the absolute value of that expression on the left. I'm going to then say the expression on the left is equal to plus or minus the c2 on the right. I'll call that plus or minus c2c. That gets us to here. It's really beautiful Beautiful mathematics. Yes, Andrea, yes. All right, and if we're good here, I'll go to the last page if we're good. Okay. And thank you for staying a little longer. Very good. Good, Matthew. All right. All right, so we're basically ready to solve for y. Okay, so what I'm going to do is I'm gonna you know, subtract this 1 to the right-hand side of this equation, which I did. And then I'm going to square both sides of the equation, and now I've got my explicit solution for y. I have my explicit solution. And now I put in the initial value. Okay. Okay, Justin, the end will be in the recording, but I think you're good, right? You're good? All right, very good, very good. So I substitute in the initial value into the equation and solve for C. C will equal 2/3. And then Y, then we get our solution to the initial value problem. Y is equal to the quantity 2/3 times 1 plus the square root of x minus 1 raised to the second power. Well, Matthew, you could plug in the initial value at any step along the way. I tend to wait until I get my explicit solution. That just square root of 4 is equal to 2. Zachary's wondering about how we got the 3. Square root of 4 equals 2. 1 plus 2 is 3. That's all right. Hey, good question, Zachary. I want everybody to be clear and comfortable with this. Are there any other good questions? Okay, let me stop the recording.